Hello, everyone. Welcome to pay attention to our work about adversarial attacks, which is efficient loss function by minimizing the detrimental effect of floating point errors on gradient-based attacks. We all know that gradient-based attacks often suffer from severely overestimating of the model's robustness. This paper reveals that the relative error in the gradients caused by floating point errors is one of the fundamental reasons for the failure of gradient-based attacks, and the relative error is directly affected by the value of capital delta, which is equal to this pi 1 minus this pi 2. The value of capital delta is always bigger than or equal to 0. Although it is hard to completely eliminate the relative error in the gradients caused by floating point errors, we can control its side effect on the gradient-based attacks. Correspondingly, we propose an efficient loss function by minimizing the detrimental effect of floating point errors on the attacks. Experimental results show that it is more efficient and reliable than other loss functions we examined across a variety different defense models. Exponential operations are vulnerable to floating point and flow errors. Let lambda be the threshold that causes E super minus lambda to underflow. The value of lambda varies with different floating point arithmetic precisions, with approximate values of 16.64, 103.28, and 744.44 for high precision, single precision, and double precision, respectively. Due to the existence of exponential operations, the gradient calculated from the crossing tree loss is also susceptible to floating point and flow errors. When z sub y not equal to z sub pi 1, the model output is already incorrect. Therefore, we only focus on the relationship between the relative error and t when z sub y equal to z sub pi 1. When capital delta bigger than or equal to lambda, and z sub y equal to z sub pi 1, the calculated gradient equal to 0, and the relative error of the calculated gradient equal to 100%. Based on the findings, we identify that the root cause of the calculated gradient equal to 0 is because of capital delta exceeding the underflow threshold lambda. We further analyze the distribution of capital delta values in different dependent models, as shown in the above picture. The result of capital delta distribution indicates that the range of capital delta values varies significantly among different defense models. It is evident that not all models suffer from floating point and flow errors due to the capital delta values exceed the threshold, and there exist other reasons associated with floating point errors because in most cases the capital delta less than lambda. So what does the relative error look like when capital delta less than lambda? A multi-iteration gradient-based attack involves adding perturbations to the input data at each iteration, leading to constant changes in the model outputs. This makes it difficult to analyze how the relative error changes when the capital delta less than lambda. Because the essence of a multi-iteration gradient-based adversarial attack is to repeatedly perform the similar operation of adding new perturbation to the input data, we can indirectly examine the effect of floating point errors on the attack's performance by analyzing the impact of such errors on a single step. To do so, we introduce the scaling factor C. By varying C while keeping the input data fixed during the gradient calculation, we can investigate relationship between the relative error and t. When k equal to 2, which means a binary classification task, the relative error is proportional to the relative error of C times P2C. We can plot the relative errors figure as shown above. Following the similar operation, we add a scale factor C to the capital delta and hold T equal to C times capital delta constant during each iteration of a multi-iteration attack. This technique allows us to access the model's robustness with the fixed T value during the whole attack, which we call FTPGD. We observe a strong correlation between the relative error and the attack's performance. Thus, the relative error is a critical factor that contributes to estimating the model's robustness. Although we cannot eliminate the relative error in the gradients caused by floating point errors due to the limitation of floating point operations, we can control a side effect on the gradient-based attacks by minimizing the relative error. As a result, we propose a new loss function, a small modification to the original cross-interval loss, which scales the logits adaptively before the softmax operation. It is straightforward to assume that since floating point errors cause the above problem, it should be possible to solve the problem by simply increasing the precision of floating point arithmetics, because it can effectively reduce the relative error in calculated gradient due to the floating point errors. To test whether this simple idea works, we evaluate the impact of different floating point arithmetic precisions including high precision, single precision, and double precision. Or the model's robustness against FTBGD with 100 iterations. As shown in this figure, the attack's performance exhibits a similar variation pattern across different precision. While increasing the floating point precision can delay attack failure due to floating point and flow errors, it incurs significant computational overhead. Therefore, increasing the floating point precision is not a solution to solve the problem caused by floating point errors. Surrogate loss functions like CNW and DRR have been proposed to work around similar problems. They avoid suffering from floating point errors by discarding exponential operations at the same time. They only use partial D elements in the new loss function, which means they discarding quite a lot of D elements. To demonstrate the effect of discarding elements of the on the attack's performance, we design an experiment to make only a fixed number of the elements participate in the calculation of the gradients by exploring floating point and flow errors. From the figure, we can see that discarding partial D elements will impair the effectiveness of the attack. This table presents a comprehensive comparison showing that a proper loss function outperforms other loss functions on all test models. Remarkably, even with only 100 iterations, a proposed loss function achieves results that are very close to the best results obtained with at least 4,900 iterations on some models. This figure shows that a proposed loss function performs more efficiently and often with orders of magnitude faster than other loss functions for successful attacks. Because a proposed loss function can be easily integrated with existing attack strategies by replacing the original loss function, it can be used to boost the capability of existing attack strategies. This figure shows the detail for the failure of attack due to floating point errors, like running error and flow errors. We select the capital Z, which is equal to Z sub y minus max A, not equal to y Z sub A, because its sign directly indicates if the attack is successful or not. The left side figure demonstrated that for samples that suffer from running error, the value of capital Z rapidly approaches to 0 in the first few iterations and then remain positive afterwards. This phenomenon suggests that the floating point running error primarily may cause attack failure when the sample becomes closer to the classical function boundaries. The right side figure shows that for samples that suffer from and flow errors, the value of capital Z remains constant throughout the attack. This phenomenon reveals that floating point running errors cause the calculated gradient to be 0, resulting in no perturbation added to the sample, which keeps the sample unchanged throughout the whole iteration and causes the attack to failure. Thank you for listening. Please come to our session if you have any questions and want to learn more about the work. Thanks.